Alright y'all, this is going to walk you through Unit 1 concept list number 5, which uses the limit definition of derivative to find derivatives of different functions. The first example is a polynomial, and we're going to use this rule by breaking it into the pieces. Okay, so the first part is we need to look at the function when x plus h is our independent variable. So where we see this x, we're going to change it to x plus h. So that looks like 6 minus the quantity x plus h getting squared. So then we want to actually square that thing. I would recommend just writing it out twice to FOIL. That's what squaring something means. And then we've got 6 minus x squared plus xh is plus 2xh. And then plus h squared again. So this ended up looking like 6 minus x squared minus 2xh minus h squared after you distribute that derivative or that negative through. Okay? Now we're going to go and just subtract the original function. Okay, because it's got two terms, remember we're going to subtract both pieces when we substitute this in. So go ahead and just copy the original there, 6 minus x squared minus 2xh minus h squared. But when we subtract this function, we've got to subtract both parts. So minus 6, but we're subtracting x squared, so that would be plus x squared divided by h. Now, nice things should happen in the top part where things cancel out. So if you look through here, we've got a positive 6 and a negative 6. Those go away. We've got a negative x squared and a positive x squared. Those go away, leaving you with just up on the top items that have h involved in it. And that's important for this to work. Because our h on the denominator right now, we can't use direct substitution because that would be dividing by 0. We've got to have that x or that h cancel out somewhere. So it's really important that we see an h in everything on the top in order for that cancellation to happen. So because there's an h in both terms, our next step is to just factor it out. Okay, so that looks like h comes out. We're writing what's left. That's negative 2x. Over here, that's a single h left over. And then those h's go away. So at this point, we've got our limit as h approaches 0 for just negative 2x minus h. And we can plug in 0 right there to give us negative 2x, and we are done. Okay, just to show you, the directions on the test are going to ask you to use this definition on some problems, but if they don't ask you for that specifically, you're welcome to use the shortcut rules. And I in fact am going to encourage you to use the shortcut to check yourself here, because there's a lot of steps in this algebra with signs that could go wrong. So if you know what the answer is supposed to look like immediately, it can help you look out for those potential mistakes. So using our shortcut rule, if I'm trying to look at the derivative of 6 minus x squared, I'm going to find the derivative of each of these separate pieces. Well, the derivative of a constant is 0, so that part goes away. And the second part, I can use my power rule. That number comes down. I'm going to take this negative 1 times 2, so that's negative 2. And then my power decreases by 1. So 2 minus 1 is 1. And there is my derivative. It matches up. We did everything right. Okay, looking at the second problem, we're going to talk about when there's a fraction involved, what to do. The process stays the same. We want to look at x plus h plugged in first. So that just looks like 3 over x plus h. No problems there. Nothing to simplify. So when we sub it in, we've got our limit as h approaches 0, just like normal. We've got 3 over x plus h, and then minus 3 over x. Here's what I'm going to encourage you to do. Because there are fractions here, I don't want to put a big division over h, because that makes it a lot harder to keep track of which denominator goes where. Instead of dividing by h, what I want you to do is rewrite it as times the reciprocal, which is 1 over h. And you can see that h is still in the denominator, so it's equivalent to the original, but this is something now I can handle this part first and multiply by that 1 over h in the end. Okay, so now what we're going to do is talk about subtracting these. In order to do so, we've got to get a common denominator. The fastest way to do that is just multiplying those two denominators together. So we know when we rewrite this, our denominator is just going to be x times this thing. I usually put the single term first, but it technically wouldn't matter. Then what you can do is this piece needs to be multiplied by here, so it's just really 3 times x is 3x. And the same thing goes. We're going to copy this sign in the middle, and then we're going to just multiply the other part of the cross. So 3 gets multiplied by this. So it's 3 times that x plus h quantity. Okay, and then I'm just bringing down that 1 over h. Then what we're going to do is simplify this piece. Parentheses mean you probably want to distribute through. You don't need to do that on the bottom, but you sure can if you'd like to. Okay, so limit as h goes to 0. And looking at this piece, it looks like 3x minus 3x minus 3h. And just to show you, if you wanted to on the bottom, you could. X squared plus xh, it doesn't really matter. Okay, because the purpose is we wanted to make sure that when we're simplifying, like I talked about on the last problem, is the h has to happen in every single term on the top. Well, that's not happening because we haven't simplified that yet. Those cancel out, and now it's working as it should. Okay, so our next step is to simplify and factor out those h's, or just simplify crossing them out, really. Okay, so this part, I'm just going to rewrite so I don't skip any steps here and lose ya. Okay, this is what's on the top, and on the bottom I've got this x squared plus xh, and then I've got this h also on the bottom. But now my h's cancel, and I can rewrite it as the limit as h approaches 0 on -3 over this x squared plus xh, and now there are no problems. I can go ahead and simplify. Okay, direct substitution, this h gets to be 0, so it's -3 over x squared. The x times 0 goes away. This is my derivative. Okay, just showing you this with the rule. If I want to talk about the derivative using this rule, the first thing I would want to do is rewrite it as 3x to the -1st power, so I can apply that power rule. So -1 times 3 is -3, and then I'm decreasing my power by 1, so -1 minus 1 is -2, and that's -3. This x squared goes to the bottom, and they match up exactly. Okay. Last problem is the weirdest. It's using a square root here. Okay, it's the weirdest because of how you have to simplify it. So if we check this out again, same process, x plus h, looks like x plus h gets plugged in there. Okay, and you can go ahead and distribute through again, or not. It's up to you. It doesn't matter. Okay, but that's what we're going to plug in our limit notation. So starting out here, limit as h goes to 0, we've got the square root of 2x plus 2h, and then we've got minus the original function, square root of 2x, all over h. Okay, so in this case, here's why it's weird. We don't have anything we can factor. We don't have common denominators that we have to simplify to be able to add our like terms. Okay, the whole thing here is we don't know what to do at this point because we're still having divided by 0, but we can't subtract these because they don't look like the same expression underneath that square root symbol. So this is where we're going to use a algebra technique called multiplying by the conjugate. And a conjugate is just an expression that makes nice things happen. Okay, and what it looks like is we're going to take both of these terms that we see and leave them alone, and the only thing that's going to switch is this sign will switch to the opposite sign. So if you see a minus, it's going to plus. If you see a plus, it's going to minus. So we're going to multiply by the conjugate, rewrite your square root of 2x plus 2h, that stays the same. Middle part goes to plus, and then square root of your 2x. But what's important is when you're multiplying by the conjugate, you have to multiply by that over itself. Okay, because it's only mathematically valid to do this if we don't change the value of the original. This real thing, even though it's super ugly, is something over itself, which is 1. When you multiply by 1, you don't change the value, so it's fair game. But the reason we're doing it is because now some nice things are going to happen for us. So we've got this times this, and there are 4 terms total, so we're going to FOIL. Okay, first times first, when those things match, the square roots essentially cancel each other out. And to explain that, I'm going to rewrite it for a second just to the side. Okay, so we know that the square root really means you've got a rational power of 1 over 2. When I am multiplying 2x plus 2h times 2x plus 2h when they both have powers of a half, the base stays the same, and my rule for my exponents is adding them. So that's 2x plus 2h to the first power, because a half plus a half is a whole. So when we are seeing these two things, as long as they match, those radical symbols really cancel each other out, leaving you just with what's underneath. And that's always going to be the case. What's also going to happen nice with conjugates is this middle term, the outside piece with the inside piece, they will always cancel out to 0. You won't ever have to worry about it. The only thing you have to worry about is first times first, which we already took care of, and last times last. So negative times a positive is a negative, and then what we just talked about applies the same way. Because these both say 2x underneath, the square roots are going to cancel each other out, leaving us just with 2x. Okay, on the bottom, we're just going to leave this h here, and we're going to leave this big mess alone, because it really wasn't the bottom causing problems other than dividing by 0. We had to make sure h's showed up in all the terms up top. Alright, bringing down this limit notation, we're almost ready to simplify. Okay, so here the x's go away like we wanted them to. We've got the limit as h goes towards 0 of 2h on the top. H times that big mess one more time here. And then those h's can go away for us to finish this out. So we've got 2 on the top. On the bottom, we've got the square root of 2x plus 2h plus the square root of 2x, and we can directly sub in that 0 now. As we do that, we've got 2 on the top, 2x plus 2 times 0, that part goes away, and it's just the square root of 2x, and then plus the square root of 2x. Because these say the same thing, we can add them to 2 over 2 square roots of 2x. Last step, those 2's cancel out. Common mistake I see is just calling this equal to the square root of 2x, but that square root of 2x was on the denominator, so it has to be 1 over that square root of 2x. And there's our derivative. Okay, let me show you what this is using the power rule. So our function was the square root of 2x. First thing you want to do with those radicals is rewrite them with that 1/2 power so we can apply that power rule. So multiplying that to the front, we've got 1/2 times that 2x being raised to the 1/2 decreased by 1, looks like negative 1/2. But because this was a 2x and not just a regular x, we have to use the chain rule and multiply by the derivative of that inside. The derivative of 2x is 2, and then we're okay to simplify. So the 1/2 and the 2 cancel each other out. So this is really 2x to the negative 1/2, and when we think about the 1/2, we know it's the square root. We think about the negative, it goes to the bottom. So this is ending up being this 2x on the bottom in a square root symbol, and with 1 on top, just like what we were talking about here. And they end up matching up. Okay, that is it for the limit notation, talking about the definition of derivative. Hope that helped.